Hi, my name is James Fabia, and my team consists of Jacob Hewitt, Pablo Colon, and myself. We have been presented with the topic of water remediation, more specifically, arsenic-contaminated drinking water. Earlier this week, I had the honor of consulting an arsenic expert, Clarkson's Department of Sustainable Environment graduate student Kyle Monahan. He will shed some light on the basics of arsenic. The following video clip is an interview I conducted with Kyle. He will answer some basic questions about arsenic and talk about his experiences. So can you give me a background about arsenic?
Arsenic is a contaminant that's found in a lot of different types of water throughout the world. And so I focus on arsenic as a aqueous or water-based contaminant, but arsenic is also found from basically particulate sources, so that's found from coal combustion in the atmosphere, and that's around 1 part per billion. Up to 16 part per billion. Then you can find it in the soils with particle-associated materials, and then also in minerals, right? So pyrite fool's gold is a common mineral that you can find it in, and other mineral deposits. So you can find it in basically every phase throughout the environment, but the one that I think is the most important for human concern is the aqueous, the water-based phase.
And where's arsenic prevalent?
So in general, in terms of water supply, arsenic is prevalent in groundwater mostly. Groundwater has reducing conditions, and it has normally contact with those source rocks I mentioned before, those minerals that contain arsenic. So it allows for arsenic concentrations to reach higher levels than otherwise available. But also, arsenic can come from mine tailings and industrial processes that generate arsenic. Arsenic was used for a long time as a wood treatment, and then also in some insecticides earlier. In some of the developing countries, they still use arsenic-based insecticides and herbicides. So one of the main, two sources of arsenic to the environment would be anthropogenic sources from industry and things like that, along with water-based, groundwater mostly based arsenic from those source minerals, so that would be natural sources.
Okay. And so, what's your experience with arsenic?
So I do research in using ceramic filtration and reactive materials in filters to remove arsenic. So I work on kind of the water treatment side of things and the geochemistry side of things. But arsenic in general, there's a lot of different research going on with it, but I kind of focus on the remediation of arsenic contamination.
And where's arsenic found in higher concentrations in the U.S.?
Mainly arsenic is found in groundwater. That's the main way that it gets into higher concentrations. We find that surface water, though, can be increased as well due to mine tailings and things like that. So waste from mines that contains these metallics or metalloids, that water that runs over that can be higher and enriched with arsenic. And other places where we find them is stuff like in the West, right, where they have these aquifers that are stressed and they have reducing conditions in them that are able to generate these higher concentrations of arsenic. So mostly we find it in the West. I mean, it can range from, over 8,000 parts per billion down to less than 1 part per billion. That's undetectable arsenic level. So there's really a high range. Globally, arsenic actually ranges 4 orders of magnitude, so that's 10 to the 4. And so that's a really wide range in concentration, from parts per billion to parts per million, and hundreds of parts per million. So it's a wide range, but mostly I would say in the U.S., the West is where the contamination mostly is. Yeah.
And is there any risk in the North Country?
I would say that it would be hard to assess it without actually sampling different wells in the North Country, but I haven't seen any data that suggests a risk. I would say that if there was any industrial waste that contained arsenic, I might be a little worried about contamination of water supply, but I haven't seen any data suggesting that there is, so I wouldn't suggest there'd be much of a risk.
Okay.
So, yeah.
In the 1970s, 1 out of every 4 children were dying before the age of 5 in Bangladesh. UNICEF and the World Bank recognized that the surface water that was being consumed was infected with harmful bacteria that caused a deadly diarrhea. In order to fix this problem, they funded projects to create tube wells to withdraw what they believed was safe drinking water. Unfortunately, UNICEF neglected to test the mineral properties of this water before opening the wells. In the 1990s, thousands of people in Bangladesh were getting symptoms of arsenic poisoning, including vomiting, discolored skin, lesions on the hands and feet, and white lines down their fingernails. The issue had been called the worst mass poisoning in history. Due to the severity of the problem, the World Health Organization declared a major public health emergency for the contaminated water in Bangladesh. After researching the problem, they discovered that the people were being poisoned by the water being drawn out of the shallow wells built in the 1970s. The World Health Organization claimed that over 45% of the population had been exposed to deadly amounts of arsenic. Out of the 7 million hand pump tube wells built in Bangladesh, over half of them were supplying water with arsenic levels over 50 micrograms per liter. This amount is incredibly large, considering the fact that the levels must be under 10 micrograms per liter in order to be considered drinkable in the United States. The arsenic is believed to have entered the water by certain types of bacteria that remove the arsenic from the earth and deposit it into the water. The problem is that the water is being consumed and will continue to be consumed by the people of Bangladesh because there is no other source of water in the area. Also, numerous crops are being contaminated by the water that is drawn from the wells, and these crops are being eaten by the community. It has been estimated that 270,000 people will die due to cancer caused by arsenic poisoning in Bangladesh. People affected by arsenic poisoning suffer an enormous social stigma in their community, as people in Bangladesh consider it a contagious disease or a curse. We hope to fix this major health issue by the use of iron absorption pills. By simply placing a pill into the water and letting it sit, we hope to rid Bangladesh of their poisoned water problem.
Now knowing the dangers that arsenic imposes to the general public, we can now consider which solution will be most effective for arsenic remediation. For the purposes of being cost-effective, we will be discussing which method have been proven to be successful in previous research studies. Iron oxides in its many different forms have proven to remove arsenic contamination well above the EPA regulated amount. Hematite is a perfect example of an iron oxide that has high sorptive capabilities on arsenic contamination, both inorganic and organic compounds. This project aims to accomplish similar results of arsenic absorption with minor modifications to the experiment. The biggest modification to the experiment would be encapsulating the iron oxide in alginate solution. Before going into the advantages that encapsulating the iron oxide in alginate solutions proposes to this experiment and the general public, it is important to consider the procedure that is taken in creating these capsules. So the first step is to weigh out a specific amount of iron oxide, which that specific amount is determined by the iron oxide's sorption capabilities on arsenic. For purposes of being consistent, we will be targeting an amount that has been proven to be effective in previous research studies. So due to intensive research, we found that 50 milligrams of hematite have proved to absorb the 100% of 100 parts per billion of arsenic contamination in solution. We will be targeting the same pH levels, arsenic contamination, and iron concentration in this research project. After you have determined the weighed out amount that you want to absorb or create into capsules, the next step would be to take that desired amount and enter it or pour it into a glass vial. The glass vial is then filled with diluted water and alginate solution. For the purposes of creating capsules of the same size or beads of the same size, the ratio of diluted water to alginate solution in the glass vial needs to be a 2-to-1 ratio. To create uniform beads of the same size, we must sonicate the vial and also run the vial through a vortex machine. Both the sonication and the vortex help create the uniform distribution of the capsules. The next step would be to use a micropipette and manually enter the beads into a petri dish containing the calcium chloride. To go on from there, the beads are left in the petri dish containing the calcium chloride for a minimum of an hour. While that is going on for an hour, the next ideal thing would be to ensure that the arsenic contamination is at the desired amount. To do so, we must start up the atomic absorption spectroscopy machine. Once we have the machine up and running, then we can put in our arsenic contamination into the machine to determine if our arsenic contamination is at the levels that we think they're at. So the next step would be to remove the beads or the capsules from the calcium chloride and place them in an environment which contains arsenic contamination at our real groundwater settings, which include ideal pH levels and ideal arsenic contamination levels. After the beads are mixed with the arsenic contamination in the groundwater settings, there is an experiment that is conducted in which the beads and the arsenic in the water is mixed thoroughly to allow the beads to move through the water to absorb as much arsenic contamination as the beads can possibly absorb, hoping that the arsenic contamination would combine or absorb through the capsule beads, absorb through the alginate to interact with the iron oxide hematite. After this takes place for a minimum of 30 minutes to an hour, the capsules are removed from the groundwater settings, and then that contaminated water is again tested through atomic absorption spectroscopy, which after running it through the machine that last time, we can determine whether or not if the test was effective. After knowing that these beads are effective, these beads can be utilized effectively and efficiently in Bangladesh. Not only are these beads cheap, effective, but they're remote. It wouldn't take much to educate the people of Bangladesh in how to use these beads and getting it to the people that need it the most. That's why there is more than enough question and more than enough interest for projects like these in efforts to help out the people that need it the most, like the people in Bangladesh.
Cut it so you can be like,
Yeah.
scientists have fun, you know?